Right, so let me move on to the next definition, which is very useful and very interesting, is conjugate elements. And this is something we will use a lot, this definition. Okay, so two elements say A and B of a group, are said to be conjugate to each other if there exists an element G not necessarily unique. There could be more than one G's which does the job. If there exists an element such that A is equal to G, B, G inverse. Okay, so this is, so if this happens, then A and B are conjugate. Okay, there may exist and a lot of time it does, there may exist G and G prime such that G is not equal to G prime, but A is equals to B, sorry, A equals to say G, B, G prime, as well as G prime, B, G prime inverse, sorry, I meant G inverse. Okay, so that's possible, but the main thing is that if two elements are related by this relationship, they are called conjugate elements. Okay? So let's make some comments about conjugation. First one is that conjugacy is an equivalence relationship. And when we study rotation group, I will show you, and you will work this out, that, for example, rotation of an object around x-axis and rotation of the same object around y-axis after you have, say, rotated your axis system from where y-axis goes to the x-axis, they're the same phenomenon, they're the same physical operation, right?
Yes, sir.
So we will see that those two operations, there is rotation by say 90 degrees by the around the x-axis and rotation by 90 degrees on the around the y-axis, they are related by a conjugate. They are conjugate elements. Where the conjugation is what we usually call a change of basis in vector calculus, and the change of basis is also known as a similarity transformation in the matrix language. Okay, so this conjugacy relationship has a lot of application. But the first thing we want to say is that conjugacy is an equivalence relationship. All right. And the second comment, I think I've said this before, but let me just say it again because it's so important, it's worth emphasizing. All equivalence classes or all equivalence relationships partition a set into disjoint subsets. But this disjoint subsets are called disjoint subsets known as equivalence classes.
Sir, in the conjugate thing, does the identity its own conjugate?
So yeah, I mean, if you have E, yeah, exactly. Yeah, you're right. Because A and B did not need to be separate, different elements. Yeah. Like doing nothing around x-axis and doing nothing around y-axis, they're essentially the same operation. Yeah. So these disjoint subsets are known as equivalence classes. So I've sneaked in a definition in the comment. And so essentially we get the equivalence classes under a conjugate relationship are called conjugacy classes. Okay, so I now want to move on to discussing examples of groups, and before we move on and do some theorems in the next class or something. So, but before we do that, do we have any questions?
Sir, I have a comment from the conjugate group. So if a group is conjugate, the group is divided into two parts except the identity. So each of the element of one part is conjugate to the other part. Is this correct?
So what do you mean if the group is conjugate?
You mentioned conjugate group.
I don't think I talked about, did I talk about conjugate? I talked about conjugate elements and conjugate classes, but I didn't talk about conjugate groups.
Oh, okay. Then
yeah, so conjugate classes don't necessarily groups. Okay, they may, but they may not necessarily make groups. Okay.
Yes, sir.
All right, cool. So the first, we are going to discuss three types of groups here. The first one would be the cyclic group or the cyclic groups. And then we will talk about the dihedral groups. And then we will talk about the symmetric groups. Symmetric or permutation groups. They're actually not exactly the same, but they're related. I'm a little confused about the names there, but we'll discuss that. All right, so first, let's discuss the cyclic groups. So they are usually denoted by Cn, and mathematicians call them something else. We will come to that shortly. So the cyclic group, for n greater or equals to 2, consists of the elements, of the following elements. So Cn has n elements, and we can call them alpha. alpha squared, alpha cubed, dot, 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 alpha raised to the power n minus 1 times alpha raised to the power n, but that is identified with the identity. So what this notation means is that, alpha to the power r is alpha composed with itself r times. Okay? So this group is called a cyclic group. And alpha is known as the generator. So the cyclic group is abelian. Right? Because, as we can see, it essentially consists of, generating, the group elements are generated by one element, right? So, if I have alpha cubed, alpha, yeah. So, what kind of elements do we have? We have just alpha to the power r, is essentially alpha compose alpha r minus alpha r compose alpha. So this is alpha r plus 1 minus alpha r plus 1. So this is 0, right? So it's an abelian group. It's
I actually have
also,
a question about this.
yeah.
What does the negative sign mean here?
What does the negative sign mean here? Oh, sorry, I completely yeah. So let's see if we can do this without using the negative sign, right? That's very right, yes. Thank you very much for keeping me honest.
I think for groups, commutator is defined as the commutator of x and y is defined as xy, x inverse, y inverse.
XY, X inverse, yeah, exactly. Yeah. So, right.
So I think for the commutator, we need two operations, like the multiplication and addition, both is required. So I think it should be the case for Lie groups, but not for like usual groups we're dealing with.
I agree completely. It was a mistake. Yeah. So if this is abelian, the way I would look at it is if you have alpha and alpha to the power r, I would just write it as alpha, dot, 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 alpha, and there are r plus 1 elements here. And this is alpha to the power r alpha, right? So that's what I would do. Yeah. Thank you very much. Yeah. We don't have an operation of adding or subtracting group elements. Very good. Very nice. Thank you. Yeah. Okay, so Cn is abelian. Cn is also isomorphic to Zn, where Zn consists of the elements 0, 1, 2, dot, 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 the integer up to n minus 1, under addition modulo n. Okay, so these groups are isomorphic.